So welcome back again to this module on I/O. We are at lecture 3 now, and I'll be discussing storage interconnect protocols. Interconnection protocols, so why do we need them? Well, if you have two devices that need to communicate and talk to each other, then you want to develop some protocols such that that communication can happen and these two devices can independently develop themselves without having to constantly be together with the other one. So in the networking world, there is the open systems communication model, and that is a 7-layer model, and you can generally look at networking protocols, but also the protocols that we will discuss here in frame of this model. And fundamentally, this model divides itself into the media layer, which is all about how do you get data from point A to point B and then the host layer, which is how do the devices actually work, and at the host layer you build the actual application models for communication. Media layer starts at the lowest level, which is physical. This is the bit layer. You have the electrical specifications. If it's on Wi-Fi, the radio specifications. Optical networking can have optical specs here. How do two points signal to each other? Clock speeds. How do they agree on a clock speed? Amount of current, voltage flowing, connector specs, and the transmitter, receiver, etc. So this is like the lowest level of communication. On top of this, you have the data link layer, and the data link is where the packet specification happens. It can be a packet or a frame. Like 8 bits form a byte, or you can have a 32-bit packet, whatever the size is, but that packet has to go from one point A to point B. And that involves acknowledgement, CRC checks for error checking, retries upon failure. It essentially tackles the problem of how do you deliver a packet between 2 points that can communicate with each other. After that, you develop the network layer, and at this point you're still dealing with a packet, but your packet could be delivered not between two direct points, but points that have to be routed from two direct links, from one link to a second link to a third link, and that deals with multiple data links and then brings in the concepts of routing, which are part of networking. Then you go to the host layer, and at this point you go beyond the packet and look at the transport layer at the lowest level, which is, talks about segments of data. So several packets together form a data segment that has to be transmitted, and here again you can have retransmissions that can be part of that, and other specifications on how the two ends agree to send full segments. And on top of that, the session, which deals with a session, which is a continuing interaction going on between two components, how to build those capabilities. Then presentation layer, which can deal with encoding, compression kind of things. And at the top of the layer is the application layer. And at the application layer, you deal with the actual work that you want to get done, which is the application level commands. So that is the 7-layer model. And for storage interconnection, we will look at the protocols today that are important. So at the core on a motherboard, there is a CPU, and the CPU communicates with other chips on the board or other adapters on the board, and it communicates with the memory using the system bus, which has its own protocol. But for other devices, there is another bus on the server, and the PCI bus, so the Peripheral Component Interconnect Express, is such a protocol to express a server bus for the CPU to communicate with peripheral devices. So this has been pretty standardized now. It provides a serial I/O interface. Serial means you send one bit at a time. There is no multiple lines, like sending a byte in multiple lines. It's one at a time. The PCI bus, however, does improve speed. It gives you one link, but you can add more than one PCI bus link, and you can have like one or the X4, which will give you 4 lanes together, and X8, which will give you 8 lanes together, up to an X16, which gives you 16 links together. And each of these links can have separately receive and send ports. So you can have full duplex communication happening at the same time. And if you needed less throughput, you would use one lane, and a lot of the things like keyboards, mouse, etc. will just need one lane. But if you are dealing with network communication, you have storage devices, and you are actually going to send a lot of data, you can use more than one lane, and accordingly you connect to the bus. So that's the PCIe bus. How does it operate? Let us get into some more details. It is basically at a transport layer, or it's the lowest level layer on the physical, the data link, and the transport layer to get data through. It doesn't in itself care about what is happening between those two devices. It cares that the communication is happening. And so there is a CPU, assume, and on the other end there is a device. And in this diagram, you have one lane, and there are 4 wires for one lane, 2 for receive, 2 for transmit. And this is called a differential pair because to receive you'll have both the plus and the minus wire, and you can more accurately get the signal at the other end if you get both of those wires, and you can see the differential difference between these two to detect the signal more accurately. So at the lowest layer here, the physical layer comes in, which has the receive and transmit circuits for PCIe specification, power management, width, lane mapping, all the electricals. Then on top of the physical layer, there is a data link layer specification for this protocol, and that deals with link management, sequence number management, error detection, error correction kind of things. And on top of that, then there's a transaction layer, which is all about assembly, disassembly of the transaction layer packets, and packet formats, header, how to get the data out of that, and so those kind of things. So here you can see PCIe has gone through generations. The most prevalent one available is PCIe Gen 3 at this point, although there are specs for PCIe Gen 4 already in place. It takes several years after a spec is in place before devices actually have support built out in the hardware for that. At PCIe 3 speeds, the clock speed is defined at 8 gigahertz. You can get 8 gigabits per second traffic or data passing between 2 devices, and that is about 1000 megabyte per second, and that converts into, if you were using 16 lanes, you'll multiply that 1000 megabytes into 16, and that gives you 16,000 megabytes a second for if you are using all the 16 lanes. So that's how it scales for communication in devices. And this is full duplex, so you multiply 16,000, and if you were going full bidirectional, you get 32,000 megabytes per second. So the PCIe protocol is the lower level protocol used on a motherboard for the CPU to communicate through to other devices. The storage layer, and originally the SCSI protocol, has been very prevalent there for device level communication, and especially with parallel devices that were connected, storage devices that were connected back to the server. And SCSI in itself has several protocols and things it does. Like on the left side, there is a architecture specification for SCSI. It's a target, there's an initiator, there's a device, how many devices you can address. There are primary basic commands defined by SPC. There are block commands for disks defined by the SBC protocols, and there are other commands defined by other specifications. So SCSI, it defines device communication commands, and it definitely includes disks, optical devices, general devices. Then SCSI in itself was available as parallel interface originally, but as things develop, there is serial SCSI, which is serial attached SCSI, which is the more prevalent one used now. And then you can also have SCSI that goes outside of your motherboard connection. And there's fiber channel protocol, so SCSI over fiber channel. There's InfiniBand, which is another transport level protocol on the network. There is IP networks, which is what we know as TCP/IP, and that is internet SCSI. So when SCSI goes over the internet as a transport layer, that's what iSCSI is. It can also float over USB or directly on top of PCIe with SCSI over PCIe, although that has not been widely popular so far. So how do you use SCSI? Here's a diagram of CPU, and it's connected to the RAM through the system memory bus. The CPU has a PCI bus, and then the PCI bus connects to a SAS host bus adapter. The disk that supports SCSI will then be connected through the host bus adapter to communicate over the SAS protocol, and that's the serial attached SCSI protocol. So you will have wires going from this adapter to disk 1 and disk 2. These two disks can be hard disks or solid state disk drives. The role of the SAS host bus adapter is to be able to connect on the PCI bus, be able to communicate with the PCI transport protocol, and then on the other side be able to communicate over a serial attached SCSI protocol with the disk. So it's doing that. When this communication happens, when the CPU sends read commands or write commands, the DMA is an important part of how communication happens with storage. That is direct memory access. So the storage device is able to directly write to areas in the RAM without the CPU having to code that part, and similarly it is able to read data from the RAM directly, and that is known as direct memory access, which is supported through the PCI bus protocol. So that's how you would put a SCSI based disk here. There is another protocol like SCSI. It is SATA serial ATA. This has its origins to more of the PC side of the business with the AT machines and IDE drives. So serial ATA is still very much prevalent. And you can have disks that can be hard disks or solid state drives that support serial ATA. Now for serial ATA, again, you need a bus adapter to sit on PCI, because SATA is not PCIe. These are two different protocols. And the adapter in between, actually for SATA cases, runs with an AHCI protocol that then runs on the PCI bus. Basically, the adapter, it translates and is able to communicate over the PCI bus with the RAM and the CPU. And on the other side, it is able to communicate with the disk that supports the serial ATA interface. A PCI system, a bus, can support multiple adapters. So you could have SATA and SAS both together. Now, when you see these together, you could also see that these protocols have some limitations. They have bandwidth levels that you can reach. The SAS protocol can get you 1200 megabytes per second, which is 12,000 gigabits per second on the SAS3 protocol. And it is able to, on a single queue or up to two queues, send up to 254 commands, and they just get queued up for the disk to process one by one. So queuing is another important concept, and you're able to send a queue of up to 254 commands on SAS. The serial ATA interface, the SATA interface, has a smaller limit in its specification. You can reach up to 600 megabytes per second or 6 gigabits per second. And the queue depth in this case is 32 that you can reach here with a single queue. So that's the slight differences between these two protocols. SAS is used definitely more in the enterprise space, and SATA is more in the desktop user laptops kind of space. So another thing that has happened with the arrival of solid state drives is that earlier solid-state drives just used an interface and used SATA and SCSI protocols so that it was easy to just get them into the system. But we did cover flash memory, and we know that it is much more capable than the bandwidths that are imposed by SATA and SCSI. So there is a new protocol, NVMe, that sits nicely right on top of the PCIe transport layer, and that gives a lot higher bandwidth and throughput. So you can get 2000 megabytes per second per lane on this protocol, and you can use more than one lane. So if you use 4 lanes, 2000 times 4 will become 8000 megabytes per second. So NVMe allows also a much deeper queue depth. You can put up to 64,000 commands ahead, and it can process those commands, and you can even have more than one queue. You can have 64,000 queues, so multiple queues and a lot of queue depth. And now it will depend on the protocol allows it, but it will ultimately depend on the device, on what it actually supports and what is meaningful for it. But the protocol has largely extended the capabilities that you can get. So NVMe also is specific to working on the non-volatile memory space. So it is not a more open-ended protocol like SCSI. It is more closed for a purpose and deals with the logical block addressing, queue management, reads, writes, flush, compares, that are more geared towards the non-volatile memory segment. It also is supported on different form factors, the M.2, the U.2, which is the regular 2.5-inch form factor that we are used to seeing, and a couple of other form factors. So here is all three combined together, and you can have all of them on the same server as well, same motherboard interconnected on the same PCI bus. There is another way to connect to storage, and this is largely if you really want to share storage. You don't want every physical compute server to have its own disks, and sometimes disks are not used on one server, but they are needed on another server. So centralization of storage helps you with those capabilities. So storage on the network can be much better divided over a bunch of servers. It does come with the cost of having to have networking equipment, as well as the latency that will come with it. But at times the cost that you pay for that is worth using those capabilities. So if you want to use storage over the network, there is the protocol SCSI over network. There is a fiber channel protocol, and fiber channel is a networking protocol that is available, and storage area networks are actually built on with SCSI running over a fiber channel protocol. So just like we had a host bus adapter for SAS, serial SCSI, in this case there will be a host bus adapter that on the other channel is communicating over fiber channel with the network devices on fiber channel, and at the other end there is still a disk that it is communicating over. So you still have a SCSI protocol going on at the application level, but now at the transport level in a storage area network you use the fiber channel protocol. The other alternative is we already have networking, local area networks, and we use IP networks for that. So you have Ethernet cards, you can use an IP network, and when you do that, it's a NAS network attached storage. So you could go that route as well. The difference between SAN and NAS is SAN has been more efficient. The fiber channel protocol, the way it is designed, is specifically for communication, like for disks, etc., and not more open-ended like the internet protocol. So it has lossless features built in that make it more efficient. So if you want high performance storage over the network, you get SAN networks. Of course, you have to buy the extra equipment for that. And otherwise, you can also use your existing IP networks and use a NAS storage. As far as the host is concerned, or the operating system, because it is still communicating over SCSI, it will still view you as a disk as if it were connected right on the on your server itself. The additional way of getting to storage is if you use a higher level protocol and you have NFS storage as well. In the case of NFS storage, you're not really accessing the disk directly now, not doing block IO anymore with the disk. You look at the disk as a file system, and you're changing a file, so you're updating a file. So you're doing more of the file IO and not the disk level. So NFS is available. Those are file system level protocols. That's also network shared storage. And the reasons for using those protocols is if you want a file system at the center that more than one computer can get access to, and you can share files, and one user reads or multiple users read the same file, and one or more users can actually edit the file. Yeah, so that's another way to use storage. So that's about it that I intended to cover on the storage interconnect protocols. Next lecture I'll have will be on Linux file systems. So now that we have the media and we know how we connect to the media, we can go back to the file system on how is actually this storage used in the system. Okay, thank you and bye for now.